Welcome. In this section, we will build an all-pass filter using op-amps and do the simulation. Let's get started. So initially, I need power supplies. So I take one voltage source, I take another, and I take a ground. I wire them up. So let me configure this as a 12-volt source, and this is also 12-volt source. And let me name the terminals. So my positive VCC is going to be this, and my negative VCC is going to be the other terminal. Great. So we have created the power supply. So I'm going to be using a very commonly used op-amp from analog devices called OP7 for this demonstration. So let me just pick up the part, OP7. So this is how the part looks. So we'll quickly give it the power supply, positive here and negative here. So the op-amp is now powered up with plus minus 12 volts. So let's now build our all-pass filter first order. Also, we need a voltage source, guitar simulator kind of stuff. So let's say I'm using a voltage source, and let me just wire this up also, and the other end will be connected to the ground. Okay, so far so good. Now we need to configure their values. So let's start with the resistors. Let this be the 10k resistor. Let this also be a 10k resistor, and this too is a 10 kilo ohm resistor, and let the capacitor be 70 nanofarad capacitor. So if you remember, and then let me just complete it. So this is the out terminal, and let's name it V out, and this is the input terminal. So let's name it V in. And if you remember, the formula for calculating frequency, which is going to undergo 90-degree phase shift, is defined by, as shown here on the screen, which is 1 divided by 2 pi RC. So in our case, R is 10 kilo ohms. This is basically R3, and capacitor is 70 nanofarad. So my frequency that's going to undergo a 90-degree phase shift, using this formula, it works out to be 227 hertz. So let me just use this same frequency. So I'm doing a sine simulation. I have no DC offset. My amplitude is plus minus 1 volt, and my frequency is 227 hertz. So this frequency, as per the earlier theory and analysis, it should undergo 90-degree phase shift. And then I have to do my transient analysis. So what I've done is that I will run the simulation for 20 milliseconds in steps of 100 nanoseconds. Also, I've configured my FFT, which we will discuss later. Let me run this simulation. Great, so this simulation runs, and let's see the input and the output. So here is the input, a sine wave at 227 hertz, and let me see what is the output. Excellent. So you can actually see that the input is a sine wave, and after 90-degree shift, it has become a cosine wave, and we can actually run an FFT on this to show that both the frequencies have been passed without any attenuation. Only the phases have been shifted. So you can see that at 227 hertz, both the frequencies have been passed by the filter, so it's all pass filter. And let's see its phase. So I can see phase from here. Let me just make this window bigger. And okay, so as you can see, I am looking the Fourier transform of the input, and my frequency is at 227 hertz, and this entire frequency component has been passed. Now, this frequency component, that is the input, is showing a phase of 90 degrees. So this is a start point, And now when I observe my V out, in V out my 227 Hertz has been passed and it added a 90 degree phase shift. So if you remember, this is almost 90 degree, and you add another 90 degree in this, so you'll get 180 degree, and this is exactly what the theory taught us. So we are in, this circuit is functioning fine, and in fact we can do more modifications to this circuit. Instead of say one stage, we can make a multiple stage, let's say a 4-stage all pass filter. So basically we will copy paste this filter multiple times. So let me just name this. So this was my final V out. So this now becomes my final V out. And in between I have, let me just call them different names. So, okay, let me just name them differently. Let's call it out 1. So first stage output. Let me call this out 2. This is the second stage. And let me call this as out 3. And my final V out is V out. So let's run this simulation once more and see what's happening. Okay, I have to include them in my FFT analysis. So let me just add these components to out 1, V out 2, and V out 3. So it's running. It's going to take some time because now a lot of FFTs have to be carried out. It'll take some time, so I will skip and move forward. Here is the input, V in, and here is the first stage output. So you can see that first stage output is 90 degree out. Then we have out 2, another 90 degree phase shift. Let me plot it with a different color. Let's say this. So this is again 90 degree phase shift, and then we have out 3, another 90 degree phase shift. This should also be with a different color. Let's say magenta. And lastly, so this green signal, if you remember, this green is our input. So our output, after suffering a 360 degree phase shift, should come back in sync with this green input. So let's see if it's happening or not. So V out, let me plot it with a different color. Let's say brown. Brilliant. So if you can see, once this green is the input and this brown is the last stage output. So in this part, the filter is trying to stabilize, and once the filter stabilizes, this brown matches with the green and they start overlapping, which means the output is now perfectly 360 degrees shifted, and both green and brown are overlapping with each other. So the filter is working beautifully, each stage giving 90 degree phase shift to a 227 hertz signal. We can also do the FFT here and see the intermediate stages. So we'll take everything, and you see the entire signal has been passed without any issues. So it's acting like an all pass filter without any trouble, and that we can also monitor from here. Once the filter stabilizes, the amplitudes at every stage are just the same, that is plus minus 1 volt. So there's no attenuation. More important is, let's see if we can have a look at the phases. So let's go to the report and let's make it bigger. So this is the FFT report, and what I wanted to show you, okay, so this is my input signal. I have a 227 hertz signal, and the phase associated with it is 90 degrees. So the V input is taken as 90 degrees. So the second stage, V out 1 here, will add another 90 degrees. So now 90 plus 90 is almost 180 degree. It is showing 178 degree. And then it should be 270 degrees. So minus 90 degrees is nothing but 270 degree. This is second stage V out. So this is actually 270 degree. And finally, we are back to our original signal. So this clearly shows that we are able to run this simulation. This entire circuit is working beautifully as a 4-stage all-pass filter, where we can implement phase shifts between 0 to 360 degrees. To prove it to you that this is actually, it can take any frequency. So I can do some modifications to this. For example, let's do this, say at 1 kilohertz. And I will have to do some modifications. Okay, I'll have to change my Fourier. So 1 kilohertz here. And I hope the rest of the things should be the same. So obviously this will not undergo 90-degree shift, but something else. So as you can see, once the filter settles down, the amplitudes of all these waveforms are just the same, plus minus 1. That means no stage is implementing any attenuation. And earlier we passed a 227 Hz signal, it didn't get attenuated. Now we have passed a 1 kHz signal and still there's no issues. So here we are. You can see that the green is the input, red is the first stage, then this pale green is Vout 2, which is this one, then magenta Vout 3, this is the magenta one, and then finally the brown Vout, which is this one. So I hope you have been able to understand this entire circuit, and this forms the backbone of phasor, flanger, chorus, and many such effects. In short, what we do is that we this frequency that you are seeing here, this formula 1 divided by 2 pi RC. Here we somehow make this R variable, and since this R is variable, this R can then be used to implement a LFO, a low frequency oscillator, which will change the notches in this filter. More about it in a different video. Thank you.